In this video, we are going to be graphing and analyzing rational functions. The definitions I have over here on the left are important that you understand before we start graphing. The first one is end behaviors. So end behaviors are basically the behavior of a graph. The behavior of the graph of a function as x approaches positive infinity or x approaches negative infinity. The next definition that we have is a horizontal asymptote. So a horizontal asymptote is a horizontal line and a horizontal line is always y equals a number where n, or that number or value, is a value that the y coordinates of a function get closer and closer to without ever equaling that value. And a little bit later on the bottom of page 2, I want you to see the horizontal asymptote summary. So we're going to be discussing those horizontal asymptotes in a little bit more detail and how to find them on the bottom of page 2. So besides horizontal asymptotes, we also have vertical asymptotes. So a vertical asymptote is a vertical line vertical lines are always x equals a number or some value, where n is a value that the x coordinate of the graph gets closer and closer to without equaling that number. Another note that I want to make with rational functions, it's a value or values that make the denominator equal to 0 but not the numerator. And I'm going to say that in most cases, and again, this is of a rational function. So rational functions are very unique. They have a lot of different forms. So for the most part, a vertical asymptote is a vertical line that the graph gets closer and closer to without ever equaling that. And the values make the denominator equal to 0, but not the numerator. So there is an exception to this rule, the second rule here. And I have an example to discuss that, to show you that later on. All right, holes. So different places, textbooks, people call it different things. So a hole is a point of discontinuity. It's also called removable discontinuity. But basically, you get a hole. The hole is actually a point, but we focus on the x-coordinate that has an x-coordinate that makes both the numerator and denominator equal to 0. So basically, there's a common factor in the numerator and denominator that contains an x. So if that happens, then there will be a hole at that point. Again, this is for of a rational function. So everything I'm talking about pretty much today has applies to rational functions. Okay, zeros. Zeros are something that we have that a lot of functions have. Not all, I will say, but zeros are basically values of x that basically make the function equal to 0. However, since we're talking about rational functions, we're going to say that these are values of x that make the numerator equal to 0, but not the denominator. Again, this is in a rational function. And these are also called your X-Intercepts. So your X-Intercept always has your value for your x, your 0 basically is here, and then your y-coordinate always is 0. So whatever value of x in the numerator makes the equation equal to 0, that is your x-coordinate, and y is your 0 is your y-coordinate. Okay, the next one that we are going to look at, our definition, is Y-intercept. So Y-intercepts are pretty easy to find. You basically just substitute 0 for x. So a Y-intercept is a point on the y-axis that has an x-coordinate of 0. So basically, you want to take whatever your function is and substitute 0 for x. And whatever number you get is your y-intercept. And again, it's a point. The x-coordinate is 0, and then the y-coordinate is whatever you get when you substitute 0 into the function. Okay, so we've got several examples here. They are all a little bit different, so please pay attention to each different example and try to focus on, I'll try to point out the differences in each one. So in this first example, example A, we have a quadratic polynomial in the numerator and the denominator. So with rational functions, a lot of times you want to factor your numerator and denominator if they can be factored. It's always a good place to start. So your x squared minus 25 is a difference of squares. It can be factored into x plus 5 and x minus 5. Your denominator can be factored into x minus 5 and x plus 3. So if we're looking at just the numerator, what values of x would make the numerator equal to 0? Well, both positive and negative 5. So if we substituted negative 5 in for x in this factor, we would get 0. If we substituted positive 5 in the factor of x minus 5, we would get 0 here. And 0 times anything would be 0. So both negative 5 or both, I should put x equals negative 5 and x equals positive 5 make the numerator equal to 0. Well, now let's look at your denominator. In the denominator, x equals 5 and x equals -3 would make the denominator equal to 0. So if we look at this equation, we can see that they both have a factor of x, or the numerator and denominator both have a factor of x minus 5. So your simplified function would actually just be x plus 5 over x plus 3, as long as x does not equal 5. So that is the 5 that we're talking about that's taken out. Now, since 5 made both the numerator and the denominator equal to 0, that means there's going to be a hole. So there will be a hole at x equals 5 on our graph. So to figure out what that value or that point is, so 5 is a point of discontinuity. It's called a removable discontinuity. But so 5 is the x-coordinate. But to find the y-coordinate, you do have to actually substitute 5 into this new function, x plus 5 over x plus 3. So 5 plus 5 over 5 plus 3 would be 10 over 8, which would reduce to 1 and 1.24, or 1 1/4. So the point 5, 1 1/4, will be actually a hole. It is not a vertical or horizontal asymptote. So when you have to graph a hole, you would actually just put an open circle. So at the point 5, 1.4, or 1 1/4, right about there, I'm going to put an open circle. All right, so what about the -5? Well, since x equals -5 made the numerator 0, but not the denominator, x equals -5 is a 0, or an X-intercept. X-intercepts have an x-coordinate of whatever that 0 is, and 0 is the y-coordinate. So we can go ahead and graph that. So -5 is a 0, which is the x-intercept, or the point -5, 0. So we can graph that point. All right, the denominator, we had x equals -3. That made the denominator equal to 0. So if we look back at our definitions, a vertical asymptote is a line, a vertical line, x equals n, where n is a value that it, okay, but going back down here, it makes the denominator, so it's a value that makes the denominator equal to 0, but not the numerator. So -3 does make the denominator equal to 0, but not the numerator. So that is going to be a vertical asymptote. I should probably write it out. Vertical asymptote, which most teachers abbreviate as VA. So VA is your vertical asymptote. Your vertical asymptote is going to be the equation x equals -3. So this is a line. It's a vertical line, and we make it typically a dotted line. This is not a point. So the function itself can never equal -3, but you are going to see when we graph the rest of this that it's going to get closer and closer to an x value of -3, but really it's never going to be equal to -3. All right, so what else? The Y-intercept. So the Y-intercept is basically the point that you get when you substitute 0 for x. So if we substituted 0 for x in either the original equation or the simplified equation, any term that has an x would automatically become 0. So you would have -25 over -15. Or if you looked at the simplified rational function, you would have 5 over 3, which is exactly what -25 over -15 would reduce to. So if we're graphing this, it would be 1 2/3 or 1.6 repeating. But I'm going to just round it to 1.7. So that is your Y-intercept. So 0, 1.7 is approximately right there. All right, so then we have our horizontal asymptote to talk about. So the horizontal asymptote as defined earlier is the value of y that is a horizontal line that has a y value, or y equals that number, but that number, the graph is getting closer and closer to as x is going to positive or negative infinity. So as x is approaching positive infinity or x is approaching negative infinity, we want to basically look at what's happening as x approaches positive infinity and negative infinity. So if we look at either equation, whether we look at the first equation or the reduced equation, f of x, I'm going to write the original one. So f of x equals x squared minus 25 in your numerator, and then x squared minus 2x minus 15 in the denominator. So as your x values are becoming very, very large or very, very small, depending on if you're going to positive infinity or negative infinity, but this is basically very, very large numbers. These terms that do not, the higher degree terms are going to get much bigger, much faster than the lower degree terms. So these lower degree terms really are going to become insignificant. So as our x values are getting closer and closer to positive and negative infinity, the function is going to be approximately equivalent to x squared over x squared. So these x squared terms, you're the highest degree term in the numerator over the highest degree term in the denominator, because these other terms are going to basically become insignificant, like I said, as we go to positive and negative infinity. Well, if we reduce x squared over x squared, we basically get 1. So your horizontal asymptote is going to be the horizontal line y equals 1, because that is the value that y is, that your output is going to get to as these x values get bigger and bigger and bigger. So we do want to, again, draw a dotted line crossing the y-axis at 1. Again, your graph is going to get closer and closer to this without ever crossing it or touching it. Or, well, actually, I take that back. It could possibly cross it, but it does, as we go to positive and negative infinity, get closer and closer to that point. All right, so we have a few points to work with. We have our horizontal and vertical asymptotes to work with. At this point, I am going to switch over to Desmos, which is a great place to kind of get an idea of what the graph looks like. And this graph is this one right here. So if I go over to the graph here, and if I also put in my vertical asymptote at x equals -3, so put a negative in there, and I'm going to make that show up. So that green line is basically our vertical asymptote. Our horizontal asymptote is the line y equals 1. Make that show up there. That's a purple line there. So, but remember, the function itself is this black line, and it has what we call branches. So if we kind of zoom in and kind of look at, so this is kind of what the graph is going to look like. It's going to be getting as from the right side as your x values, and we can look at this with if I click on it and drag it, you can see that your x values, if we just focus on the x values, they are getting closer to a value of 3. And if I zoom in or zoom out, and move it up and click on this, you can still see that those x values are getting closer and closer to -3, but it never actually equals -3. Now, if we focus on the y values, as those x values are getting closer and closer to -3 on the right, what's happening to the x values? Where the x values are just getting bigger and bigger and bigger and bigger. So if we go back to this screen now, if I want to, oops, I didn't mean to do that. If I want to draw my graph, I now have an idea of what this looks like. Now it's going to be getting closer and closer to, so we talked about this branch over here. It's getting closer and closer to -3. It's as the x values get closer and closer to -3, the y values are going to keep increasing. On the right side, as we're going to positive, as the x values are getting bigger and bigger, this branch is going to be getting closer and closer to a y value of 1. Again, we can look at that on our Desmos screen here. So if we're looking at this branch off to the right, you can see that, oops. So it kind of changes direction here. It's getting closer and closer to the purple line. That purple line represents the line y equals 1. And as we zoom in, you can see that that purple line is always below that black line. So it is getting closer and closer to it. If we look at the y coordinate, or the x coordinates, and the y coordinates, actually, the x coordinates just keep getting bigger and bigger. But look at the y coordinate. The y coordinate is getting very, very close to 1, but it never is equal to 1. It's so here we have 1.0, and we move back, we get 1.1. So it's important to notice that the x values are going to be going to positive infinity, but the y values are getting closer and closer to 1. And we are actually going to put that on our graph. So each end of this branch we're going to describe as, whoops, not x, as x. I just keep wanting to write x. As x approaches -3 from the right. Now there is a way to symbolize that you're talking about x approaching -3 from the right, and that's with like a superscript up here. We're going to put a little plus sign. So this notation right here means x approaching -3 from the right. So as x is approaching -3 from the right side of the graph, the function f of x is going to, or the f of x is basically your y coordinates. So the y coordinates, we're going to positive infinity. And on this end of the branch, so this side, what are your x values doing? Your x values are getting bigger and bigger and bigger. So the x values are approaching positive infinity. Your y values, or your f of x, is approaching 1. Now it is approaching 1 from above. And most, that might not be important for many things, but it is, but it might be important in some cases for you to understand that that's from above. All right, so now let's look at our other branch. There's going to be a second branch over here on this side, and it's going to be going down and getting closer and closer to the line x equals -3 from the right, and getting closer and closer to this horizontal asymptote as it gets smaller and smaller. So if we look at this on Desmos and we focus in on this branch over here, you can see that it is crossing the x-axis at -5, and then it's getting closer as we go up and to the left. We're getting closer and closer to that purple line, which is y equals 1. If I click and drag here, you can see that the y coordinates are getting closer and closer to 1, but your x values just keep going further and further in the negative direction. As we go down the graph, your x coordinate now is getting closer and closer to -3, but your y coordinates are going to negative infinity. So they're just going down and down. So, but your x coordinate again is getting closer and closer to that -3. So if you have to describe your end behaviors on this side, as x is approaching negative infinity, the graph of f of x is approaching 1 from below. And then this end of the branch, as x approaches -3, but it's coming from the left side. So to symbolize that, we're going to have that little negative here. This just means from the left. The graph is going down, down, and down. So that graph, f of x, is approaching negative infinity. All right, so one other comment that I'd like to make is your domain and your range. So zoom out here a little bit so we can kind of see the overall picture. Oops, I didn't mean to do that. All right, so your domain and your range are what values, the values of that x and y are allowed to be. So if you look at your x values, your graph gets closer and closer to -3, but will never be -3. But it does go off to positive infinity on the right and negative infinity on the left. So if we also look at our original factored function, we had two factors in the denominator, x minus 5 and x plus 3. So x cannot equal 5 because we cannot have a denominator that's equal to 0, but x can also not equal -3. So your domain would include all real numbers except 5 and -3. So I'm just going to say it simply that x cannot equal 5 or -3. Now, there are different ways of writing your domain and range in other classes, but I'm just going to keep it simple. Now, your range, your y values. So the graph does keep going up and down forever and ever, but it will never have a y value of 1 because your graph is getting closer and closer to a y value of 1 from above and below, but it's never actually going to equal positive 1. So your range would be all real numbers except y cannot equal positive 1. So if you have to state your domain and range, that's what you would have. Okay, so I know there's a lot going on there, so try to take it in, listen to it again if you need to, but we're going to go on to example B here, which is a little bit different. Every single one of these examples has something different or unique about it. So I know that this is going to be a long video, but it will cover all the different scenarios that you might face. All right, so in example B, we have a numerator that cannot be factored. So we're just going to rewrite this as x minus 5. But your denominator can be factored into x plus 5 and x minus 3. So we do not have a factor we do not have an x value that would make both the numerator and denominator equal to 0, so there will be no holes, which is nice. But if we look at the numerator, what value of x would make the numerator equal to 0? 5. So x equals 5 will be a 0 or an X-intercept at the point 5, 0. So we can go ahead and graph that point right away, get that over with. And then since your denominator has two factors with x, there will be two x values that will make your denominator equivalent to 0. So x equals -5 and x equals +3. Both of them would make the denominator equal to 0. So these would be undefined values. But they're going to both be vertical asymptotes. So these are both vertical asymptotes. So in this problem, we're going to have two vertical asymptotes. X equals -5, again, is a line, a vertical line that goes through the x-axis at -5. And x equals +3 is a vertical line. It's not a point. It's a line that goes through the x-axis at +3. So all of those points have x values of 3. All right, so now let's think about and we did mention that there's no holes. And that was because there isn't an x value that would make both the numerator and denominator equal to 0. But we will have a horizontal asymptote. So if we think about what's going to happen as x approaches positive infinity or x approaches negative infinity, what's going to happen? So our g of x function is going to be approximately, so if we look back at the original one, as these x values are getting bigger and bigger and bigger, the -5 in the numerator is going to become insignificant, so will the 2x minus 15. So we basically get down to just x over x squared, so that's the highest degree term in the numerator and the highest degree term in the denominator. Well, if we reduce x over x squared, we get 1 over x, the fraction 1 over x. So if we think about what's going to happen if we put a very large positive number in there. So even though infinity is a concept, think about putting a very, very large number in there. Well, if you're dividing 1 by a very, very large number, it's going to be getting closer and closer to 0. The same will happen if you put, but it still would be a positive. It would be still from above, though. If you put a negative infinity in the graph, and you kind of think about this as dividing 1 by a negative, very, very large negative number, it will be approaching 0 again, but from below. So I just have a little plus sign because it's coming from above. This one should be coming from below, but we'll look at that in the graph and see if that actually holds true. So so both of those are approaching 0. So your horizontal asymptote then is going to be the horizontal line y equals 0, which is the x-axis. All right, so what else do we have to do here? So we kind of need some more points here. The y-intercept. Forgot about that. So the y-intercept, if I look back at my original equation, I put 0 in for all the terms that have x. So g of 0 would basically boil down to -5 over -15, which would reduce to 1/3. So your x-intercept is the point 0 and then 0.3 repeating, or 1/3. So that's another point that we can graph. So 0.3 is going to be approximately right there. Kind of made that too big. All right, so we've got the x-intercept, the y-intercept, our asymptotes. So there's a lot of empty space here. So we could plug and chug numbers into our equation here. Or we can, in this case, we're going to just kind of simplify this a little bit. We're going to look at Desmos. We're going to get rid of these extra lines. Let's see. So instead of y equals 0, now our horizontal asymptote is going to be or instead of y equals 1, it's y equals 0. Our vertical asymptote, we're going to have 2 of them at x equals -5, but also I'm going to add didn't mean to do that. Equals 0. But we'll have another one at, right here. I knew I had one already set up. Okay, so x equals 3 is the other vertical asymptote. And let me find the graph of x minus 5. It's right here. Okay, so let's zoom out a little bit so you can kind of see what the graph looks like. So the green graph, you kind of have this kind of parabola-shaped kind of thing that looks like a bowl in the top above the x-axis, and then you have this going down to the left and up to the right, and this one going down to the down here and up here. So there is something interesting though. If you look at let's talk about this section on top here. So if we trace the points, and we look at the x-coordinates, the x-coordinates are getting closer and closer to -5, but it never really equals -5. Your y-coordinates are just getting bigger and bigger and bigger. On the other side, we look at the x-coordinates, and you can see they're getting closer and closer to 3, but the y-coordinates are just getting bigger and bigger and bigger. So going back to my graph here, I'm just going to try to mimic that graph. It's going to get closer and closer there, and we kind of had a bowl-shaped thing, and it gets closer and closer over here. So if I want to talk about what's happening at these branch ends of these branches, we would say as x approaches, the x value here is -5, g of x is approaching positive infinity. On this end of the branch, as x approaches 3, then g of x is approaching positive infinity also. Now it is approaching -5. This left side is approaching -5 from the right. So we're going to put a little plus sign there. This branch is approaching positive 3 from the left. So we'll put a little negative there to show that it does that. All right, so let's look at the section that was over here. So going back to Desmos, if we look at this branch of it, and we look at the x values, if you notice, the x values are getting closer and closer to -5, but the y values are getting smaller and smaller and smaller. If we go in this direction, your x values are getting smaller and smaller and smaller, but your y values are actually getting closer and closer to 0. Okay, so we'll go back to our graph. And it would kind of be nice to have at least one point. So if I zoom into this graph, let's see, this would be approximately the point -6, -1, I think right here. Yeah, or about -6, -1. So I'm going to go ahead and graph that point. It might not be exact, but it gives me at least a place to start and get closer and closer that way. Now your lines should not cross unless you have something special happening like we do on the other side. So on the other side, we do have an X-intercept at 5. So let's take a closer look at that graph, and let's see what's actually happening at 5. So normally this graph would continue running along that purple line of y equals 0, but it would stay below it. Well, this is a special case where it actually crosses the x-axis at 5, and then it's going to be above the x-axis or above the line y equals 0, or your horizontal asymptote. So that one's kind of tricky. So going back over here, it actually, like I said, goes above the x-axis, but it's going to run right along the x-axis, but it's going to be above it. This one does, however, keep getting closer and closer to an x value of 3. All right, so let's describe each of these ends here. So as x approaches -infinity on this side, the function g of x is approaching 0. On this end, we saw that as x is approaching -5, now approaching -5 from the left, so we're going to put a little negative up there, then g of x is approaching -infinity, because the g of x is the y values. They're going down, getting smaller and smaller and smaller. This branch, as x is getting closer and closer to 3, g of x is getting closer, is going to -infinity, so it's just getting smaller and smaller. And then up here, even though it crossed the graph, this one was kind of tricky, but x is approaching positive infinity. The graph of g of x is approaching 0, but it's not approaching it from above, or from below, like we thought. So this actually ended up not being true. It's from above, because it did cross the x-axis at 5. So some of these rational functions have some strange behaviors. So you really have to kind of look at the graphs to get a better understanding of what they're going to look like. Okay, so that's our second example, but you can see how different this graph is than this graph. The next one is also going to be very different from the last two. Use blue this time. So your h of x equals x squared minus 25 over x plus 3, so that can be factored into x plus 5, x minus 5 over x plus 3. So what values are going to make the numerator equal to 0? Negative 5 and positive 5. So x equals negative 5 and x equals positive 5 are your zeros. So there are going to be two zeros, or two x-intercepts, at both positive 5 and at negative 5. What values of x are going to make the denominator equal to 0? Well, that would be negative 3. So x equals negative 3 is going to be a vertical asymptote. Okay, and then if we look at, to try to find the horizontal asymptote, again, we want to think about what's going to happen as x is approaching positive or negative infinity. So if we look at our original equation here, h of x, if we are going to positive or negative infinity, the minus 25 and the plus 3 are going to become very insignificant, and we just really have to focus on the highest degree term from each, which would be x squared over x. And if we reduce this, we get x. So, and I should say squiggly equals there. It's not actually equal to, but it's approximately the value of x squared over x, or x. So what would happen then if you put a positive or a negative, or let's start with positive infinity. So if we put positive infinity, or a very, very large number in for x, it's going to equal the same thing, or positive infinity. If you put a negative infinity in for x, or a very, very small number in the negative direction, it would be going to negative infinity. So we really don't have a value that the y is getting closer and closer to, like we did here with 0, or like previously with 1. So when this happens, there is going to be no, so if your graph is going to be going to positive infinity or negative infinity, there is no horizontal asymptote. So we're almost to this horizontal asymptote summary here, which will discuss the three different possibilities with horizontal asymptotes. All right, so we've got our vertical asymptote, we got our horizontal asymptote is none, we've got our x-intercepts. Now let's discuss the y-intercept. So again, the y-intercept is what you get when you substitute 0 into our function. So if I put 0 in the place of the x's, it all boils down to the constants, negative 25 over 3, which would be negative 8 1/3, or approximately negative 8.3 repeating. So remember, 0 is the x coordinate, negative 8.3 repeating would be our y coordinate. So that is right here. Okay, so we don't have a whole lot to go by. We could, we've got our x-intercepts, our y-intercept. We could, again, substitute values in for x and y. But let's kind of look at what the graph looks like on Desmos. So we're looking for, we're going to get rid of that. We still have a vertical asymptote at x equals negative 3. Not at negative 5. We do not have a horizontal asymptote. And I'm looking for the x squared minus 5. No, just x minus 5. I passed it up. There it is. Over x squared plus 2x minus 5, minus 15. Or no, that's the one we did last time. I'm looking for the x squared minus 5 over x plus 3. There we are. Okay, so now let's see what this graph looks like. I'm going to zoom out a bit. All right, so we've got our vertical asymptote there. We've got our X-intercept here at negative 5, 0, and negative 5, 0, positive 5, 0, our Y-intercept at negative 8.3. And you can kind of see that if we scroll out, it kind of looks like these two pieces would kind of make a line, a diagonal line. So even though we don't have a horizontal asymptote, this particular graph does have an oblique asymptote. So I'm just going to try to quickly explain to you how to find that oblique asymptote, because it is something that you will do in pre-calculus. Oblique asymptote. So to find your oblique asymptote, you basically want to divide your x squared minus 25 by x plus 3. So x squared minus 25 divided by x plus 3. So this takes us way back to polynomials and dividing polynomials. When you're dividing by a binomial x plus 3, we can use synthetic division. Put your negative 3 out front, then use the coefficients of the polynomial that you're dividing by, or that you're dividing. Our leading coefficient is 1, our middle coefficient would be 0, and our constant would be negative 25. Then if I go through this process of synthetic division, I'd bring down the 1, negative 3, 9, and negative 14. So the negative 14 is our remainder. So so technically when we divide this, we would get x minus 3 minus or plus negative 14 over x plus 3, since that's what we're dividing by. But your oblique asymptote, so your OA, is actually going to be the diagonal line y equals this part, x minus 3. So x minus 3 has a y-intercept of negative 3 and a slope of 1. So if I were to graph that, and this is, again, an asymptote, so we want to make it a dotted line, not a solid line, it would basically run right along that that graph. So this does kind of help us with our graph a little bit more, because from this point, it's going to be getting closer and closer to that diagonal line. On this side, however, remember this vertical asymptote does continue going down, so it's going to get closer and closer to that vertical asymptote. Over here, this point is going to be getting closer and closer to the line x equals negative 3, and as it goes down, it's going to get closer and closer to this diagonal line. So there isn't a horizontal asymptote, but like I said, there is an oblique asymptote, which is, again, kind of interesting, different. So if I go back to my Desmos here and I put in y equals x minus 3, and we show you what that line looks like, you can see that that is definitely the line, that purple line that runs right along that blue, or well, actually they're both purple. It'd be nice if they're different color, but they do run right along those branches. So that is what we call an oblique asymptote. All right. I think I forgot to do domain and range. Going back to example B, your domain basically is all the x values except for your undefined values, which will be negative 5 and 3. So you will not have any points that have an x value of negative 5 or positive 3. So I'm just going to tuck that up here. Domain would be x not equal to negative 5 and x not equal to 3. Your range, since there is a horizontal asymptote, normally we would say your range would not be able to be equal to 0. However, we had an x-intercept at the point 5, 0. So this point does have a y-coordinate of 0, and the graph does go up forever and ever, down forever and ever. So your range is actually all real numbers. So if you have a horizontal asymptote, usually your range is all real numbers except for the y value of that horizontal asymptote. But again, this one's kind of a unique one because it has an x-intercept that does have a y-coordinate of 0, so that does not apply here. All right, so now in this graph domain, the only value that x cannot be is -3, because that's your vertical asymptote. So your domain would be all real numbers except for -3. Your range, though, it does continue to go up and down forever and ever. So your range would, again, be all real numbers. If I describe the ends of each of these branches, I would say as x is getting closer and closer to -3, from the left, the function h of x is approaching positive infinity. If I look at this branch, I would say as x approaches negative infinity, because it's going farther and farther to the left, the function, not f, h of x is also approaching negative infinity. So that's kind of your ends of that side. On this side, as x is approaching -3 from the right, your y values, or h of x, is approaching negative infinity. And then up here, as x is approaching positive infinity, h of x is also approaching positive infinity. All right, so I think I've covered everything here. So now, summary of horizontal asymptotes. So mostly there are 3 possibilities. If the degree of the numerator is greater than the degree of the denominator, then there will be no horizontal asymptote. So that's scenario number 1. If, however, the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is the line y equals 0. So no horizontal asymptote when the degree of the numerator is bigger than the degree of the denominator, and we kind of saw that in example C here. The degree of the numerator was 2, the degree of the denominator was 1, so since the numerator had a larger degree, there was no horizontal asymptote. In this one here, example B, the degree of the numerator was 1, the degree of the denominator was 2. So the degree of the denominator is larger than the degree of the numerator, so your horizontal asymptote was y equals 0. Well, the third scenario is, what if they are the same? So if the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is going to be the equation y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So that might sound a little complicated, so I'm going to show you a couple quick examples. So let's say you have an example of f of x equals 6x to the 5th minus 7x over 2x to the 5th plus 3. So again, as you're approaching positive or negative infinity, these terms basically go away. So your f of x is going to be very close to the graph of 6x to the 5th over 2x to the 5th. But again, those x to the 5ths are the same. So when you reduce, you just get 6 over 2 or 3. So your horizontal asymptote would be the line y equals 3. So be careful when you have the same degree in the numerator and the denominator. you take those leading coefficients and y equals that. Okay, 2 more examples to go. This is example D. And in example D, we have the numerator is a degree of 2, the denominator is a degree of 1. So if the numerator has a degree that's larger than the denominator, then there will be no horizontal asymptote. So we can state that right now. There would probably be an oblique asymptote. Actually, I don't think we oh, yes, we do need to do this one. I forgot. There will be no horizontal asymptote. I was thinking it was going to be the same as the last one, but it's not, because when we factor it, you're going to see that the numerator is going to factor into x minus 5, x plus 3 over x plus 3. So we have a common factor in the numerator and the denominator. So if you look at these factors, an x value of -3 would make both the numerator and denominator equal to 0. So earlier we said when that happens, you have a hole. So there is a hole in our graph at x equals -3. If you reduce this j of x function, so j of x, if I reduce this and the x plus 3 is reduced, I would get x minus 5, but I have to keep in mind, in order to keep this equivalent, x cannot equal -3. But we do need to kind of substitute that -3 into our new simplified equation just to see where that hole or open circle is going to be. So if I substitute, no, it's j. If I substitute -3 into our new function, I would get -8. So our hole, or our point of discontinuity or removable discontinuity, is at x equals -3, but it is actually the point -3, -8. So at the point -3, -8, you are going to have an open circle on your graph. So if we talk about what's left, so what we have left, j of x equals x minus 5. Well, the equation y equals x minus 5 is just a linear equation. It has a y-intercept of -5 and a slope of +1. We could also find our X-intercept. So if we think of going back to our rational function, what value of x is going to make the numerator equal to 0? Well, 5. So x equals 5 is going to be your 0, or your X-intercept. So that is important. So we're going to have an X-intercept at +5. We have a Y-intercept at -5. And we basically just have a line with a hole at the point -3, -8. So once again, you can see that these rational functions are very unique. They all have different, there's a lot that have different shapes and forms. All right, so now as far as domain and range. So the domain, our x value cannot be -3. So x cannot equal -3 because that's the only value that would make the denominator equal to 0. But you do have a range that's not going to be all real numbers, because since this point has an x value of -3 and has a y value, or the hole has a y value of -8, there is no other point on the graph that would have a y value of -8. So your range would be all y's except for -8. So that does affect our range. All right, one more example, and then we are done. Okay, so this one I'm try to speed through here, but this is example E. If I factored this, I would get x plus 5 and x minus 3 in the numerator. In the denominator, I would factor this into x minus 3 and x minus 3. So we have a situation here where we have an x minus 3 in both the numerator and denominator. So does this mean we have a whole? Actually, no, because you have, there's another factor of x minus 3 in the denominator. So when we reduce this function, we would get k of x equals x plus 5 over x minus 3. So we still have an x minus 3 in the denominator. So this is actually going to be a vertical asymptote at x equals 3, because 3 would make the denominator equal to 0. What would make the numerator equal to 0? Negative 5. So there will be, so x equals negative 5 is a 0, or X-intercept. But there is a situation like this, or you could possibly see a situation like this. So if that happens, you need to know whether that it's not actually a whole, it's going to be a vertical asymptote at x equals 3. And we have our X-intercept at negative 5. All right, so what about a horizontal asymptote? So our horizontal asymptote, if we look at the degree, the largest term, the term with the largest degree in the numerator, we have an x squared, denominator is x squared, so they are the same, which means y is going to equal the leading coefficient of your numerator, which is 1, over the leading coefficient of your denominator, which is also 1. So we basically just get y equals 1 as our horizontal asymptote. If we have to find our y-intercept, we would substitute 0 into our function, which basically would boil down to just our constants, negative 15 over 9. Or if you looked at your new reduced function, it would be positive 5 over negative 3, which, again, these would equal the same thing. It would be a negative 1 2/3, or negative 1.7 approximately. All right, so just to help us graph this a little bit faster, so we have y equals 1 as our horizontal asymptote. We have x equals 3 as our vertical asymptote. We have this function here. So we need to turn off this one here. And we're going to kind of zoom into this so we can kind of see it a little bit closer and what's going on. Okay, so as we expected, that it's going to be getting, it's above the line y equals 1 here. It's getting closer to your x value of 3. As it goes up, it's getting closer to a y value of 1 as it's going to the right. Here, it's getting closer to your y value of 1 from below, and closer to an x value of 3 from the left. So if we were to zoom out and kind of just trace those points, you can kind of look at those x values. You can see that they're getting closer and closer to 3, but really not equaling 3. And the y values are just getting bigger and bigger. Over down here, we can see that our x values are getting bigger and bigger, but our y values are getting closer and closer to 1 from above, but they are all just a little bit bigger than 1. Over here, if we go down, let's move this up a little bit. So if we go down the graph here, we can see that our x value is getting closer and closer to 3, and our y value is just getting smaller and smaller and smaller. It's going to negative infinity. On the left side here, you can see your x values are getting smaller and smaller and smaller. Your y values are getting closer and closer to 1. So there's 0.8, but they are just a little bit below the value of 1. So let's finish up this graph. So we're going to have this here. Oh, I probably should have picked up at least 1 point from the other graph. I do have one, let's see, 5, 5. The 0.55 actually was a point on the graph. If I went back to Desmos, I would see that. You can also substitute different x values to try to figure out some other points on the graph. All right, so let's talk about our end behaviors. So as x now is approaching negative infinity, your function or y value is approaching positive 1 from below. On this end, as x approaches positive 3 from the left, your k of x is approaching negative infinity. This one up here, as x is approaching 3 from the right, your function k of x is approaching positive infinity. And last branch over here, as x approaches positive infinity, your function k of x is approaching a y value of 1. All right, so that concludes our video over graphing rational